Welcome everybody. So today we will continue a bit on this major phenomena that we can observe in machine learning, and of course one very important one is the fact of overfitting and underfitting. That's something we're gonna look at today, and I again want to start from linear models where we can see these effects very clearly. I hope on Zoom you can also hear me and ask in the chat anytime. All right, thanks guys. So then I think we are ready almost. Sorry, one. Okay. Also, don't forget to put your name for the exercise classes on Thursday. Please do that today. So, okay, least squares. So we will look again at linear models, and the reason we are interested in this is because they're showing all these fundamental phenomena, and they also work pretty well. Like if you have even very complex prediction problems, you can actually fit them well with a complex enough linear model. We always think that linear models are not good, right? They're too simple, but actually that's not the case. They can be extremely powerful depending on what features you put in, and that's also something we're gonna look at in the lab of this week. So that depending what features you use, you can fit anything, and that's what we're gonna discuss today a bit more also in the second part of today's lecture. Okay, but for now, we want to talk about least squares, which is linear regression, and we want to find a way to find a solution to this problem explicitly. So that's the question here. Can we find a solution? Of course, you can run gradient descent. That's always possible. But can you find a solution directly? So without running any iterative algorithm, is there a closed form solution? That is the question here. And to motivate this a bit more, so what we want to do is we just want to find the optimal weights, and we have done this, right? We have done this, for example, in this most simple case of a one parameter model, where we were just, well, in any case, you're just minimizing the loss function. And for example, you can take mean squared error of your model, and in that case, what we had was just the sum of all data points. And then we had the loss of each data point. So the loss is just very simple. It's the truth, right? The observed value minus the model. And here we take the simplest model of all, just W0 squared. So this is a one parameter model. Yeah, almost too simple to be interesting, but in this case, it is actually interesting to illustrate again what is happening for us. Sorry. Just as an example. So how could we solve this explicitly? If you just look at this, do you see a way to find the best W directly by looking at it without running an optimization algorithm? Any ideas? Yes, you can put the derivative equal to 0. Anything else we need to check, or if we do this, is this enough? Yeah, so last week exactly we had this optimality condition. We said that if it's convex and the derivative is 0, then you're optimal. So let's try this. That's exactly what we had in mind. So first you check if it's convex. So So is it convex in W? Anyone? Yes, it is. And we will get back to several ways to check this, but you can easily convince yourself that yes, this is convex in W. Second, yeah, can we set the derivative with respect to W to 0? And again, this is a good example to think again what this thing was, right? So the sum, of course, remains there. Then you have all the y(n)s minus. So now I take the derivative of one function here. What remains is what was in the bracket, and then what comes out is the inner derivative, and the 1/2 has just been cancelled with the 2 coming down. So now here's the inner derivative, that's -1, because we take derivative with respect to W. So all that is actually W0 minus the average of all these labels. So this y(n)s, right? They just get averaged, and this you know this. So this we have actually seen before when we talked about step sizes when gradient descent. We saw that this is the true solution to finding this one parameter to fit all these one-dimensional points here. Question on Zoom? Yeah. Very good. So they ask to remind us ourselves of the dimensions we have of all these objects here, which is always a good thing to do. So here everything is one-dimensional. So of course yn is a number. It's always a number, the label we want to predict. And the model here is just a real number. So because it's a one parameter model. So thanks for the question. So this is a real number. Of course, the model always has to predict a real number, but here it also only has one parameter to do that. So, but the output of the model, of course, is always one parameter. What else do we have? Yeah, everything here is one-dimensional. But there's lots of data points, of course. Does that make sense? All right. What else? So now we set this whole thing to 0, actually. So I force this derivative to be 0. And then we get what we just said. So then we said that the best W turns out to be the average. So this is our closed form solution, which is quite nice, right? So now we don't need to run any optimizer. We just have this solution here explicitly. So yeah, why don't we always do this? This is a good idea. It's just that we can only do this for kind of simple models. But here, and simple in the sense that, for example, we applied our first order optimality condition we saw last week. Because here the model was simple in the sense that it's convex, and also the derivative setting to 0 was easy for us to do, so we did it. And what we obtained was this global optimum, which is of course nice. Any question on this motivating example? Then the general recipe is really just that, just exactly what we said. So step 1, you try to show that it's convex, and step 2, set the gradient to 0. So that's basically what is happening here. And yeah, you can always compute the gradient. You can always look at this equation set. The question is, can you actually solve it, right? So, and here we were able to solve this equation for W. That's not always so easy, but here, if you have a linear model with least squares, then it was easy for us to do. Well, we did it only for one parameter, so now we have to do it for real for the case of many parameters. does that make sense for the next step to do? Okay, so in the case when you have many parameters in the model, then this procedure is called the normal equations for least squares. So it's just a name, and we will get to it why it has this name. But it's really just what he said, like check its convex and then solve the gradient equals 0 problem. So let's do it. And again, the key part here is that we are looking at linear models. So now again, for people on the Zoom, encouraging me to be precise about the dimensions of all my objects. So that's good. Let's do it again. So of course, the whole thing here is the model answers a number given the x data point of which is a vector, right? So the model here is a d vector, and the data point is also a d vector. So yeah, now it's actually interesting. So now we have these d-dimensional vectors. For every data point has d features. That's why we write it like this. And then of course the label is just a number. And this we have seen already, right? This is just have a linear model, and then as what cost function do you want to have on top of that? Here we want least squares error. So yeah, we just rewrote this a little bit because actually we are familiar with this, right? So this vector here, we always call this arrow vector, right? Which collects for you, for every data point n, collects how far you were off, too low or too high in your prediction. And then, I mean, if you want the whole thing, you can also write it as this a norm if you want. I mean, just notation, it's nothing special here, but if you want, you can write it as the Euclidean norm of the error vector. So y right, this is the same thing, right? The two things are in the inner product, so that it's the same thing as asking what is the squared norm. So nothing has happened here. We just do this for convenience, and you also recall what the data matrix is. The notation we always use is that every row of our data matrix collects a data point. So this is the data point x2, and because vectors are usually column vectors for us, it's up to you if you want to decide if that's maybe this is a row vector, right? So maybe I better write x2 transpose if I want to have this row here, but that's just cosmetics. Yeah. Okay, so this is really nothing new. We had this already. We had least squares, we had linear models. Now the two things we really have to do is to check if this is convex. So the L is convex in W or not. And then compute the derivative, which we have already done, and set it to 0. So how about checking convexity? So that's step 1. And here again, I can give you one of the several ways to do it. So it's really as you prefer, there's several possibilities. So one way is to look at the structure of this thing. So if you look at the function here, then it's a sum of things of actually these individual loss functions, and that's what's happening here. So if you look at these guys here, so these are like the individual loss functions ln of the weights, right? And now what we're trying to do here is to say that each of those individual ones is convex. If that's true, then their sum is also convex. So that's one attempt you can do, trying to break it down into smaller pieces. So So that's one way. And yeah, what do you think? If you look at this one of these terms, is it convex or not? So so if this inner thing here were just two numbers, x and w, then it would be quite clear, right? Then it would be, okay, I scale my number w, and then I square it. So then it would be very clear, because taking the square of a number is a convex function. And before that, there was just a linear rescaling, so that actually preserves convexity. So, and that you can also convince yourself in this case, when x is not just a number but several of them, then this still holds. So what we have here is this vector gets applied with a linear mapping, so it just gets linearly mapped to a number, and then it gets squared, and it also gets subtracted from the w. So if you know this fact, I mean, we haven't proved it, but that you can compose a linear function with a convex function, that then you still have a convex function, then that's one way to show that this guy is a convex function. You might actually ask if I can take any convex function and stick it into another convex function, and then the composition is also convex. But that's actually not true. So it's not this. You can think about it if you want. There's some easy counterexamples. So I mean, what's happening here is like we are reparameterizing our thing that we have the w, right? And then we feed it into the next convex function. So if you do this linearly, it's okay, but convex after convex is not necessarily okay to build these compositions. So composing of a linear function with a convex function is okay. Okay, maybe that's a bit obscure because you might or might not trust this rule. If you do not trust this, then it's actually easy to check if you want. So you can check this rule as an exercise if you're interested. But if you don't trust it, then I will also give you other ways to show that this whole object is convex. Is there any question on this first way? Or should we look at the second way? All right, so the second idea is is a bit more direct. So you just directly verify the definition. And the definition, that's the one with this with the 2 points on the line segment, right? That's the kind of point-wise definition of convexity, and you can verify this one. Let's try if you can do this. That is a bit of a hassle, but what we need to do, you remember. So I just want to illustrate. We have 2 points, right? W, and the other one I can call it maybe W prime. And then here is my function. I want to prove it's convex. So what I need to do is to show that any convex combination of these two function values, any convex combination lies above the purple line here. Then so that's what it means to satisfy this definition, right? Which you all know from last week or from earlier courses you had. So that's what it means here, to be smaller than 1, right? You just want, so this is the red guy that's written here, right? Lambda times this value and minus 1 minus lambda the other value. That's the red stuff. And then this one is the purple one, which you want to be below 0. Okay, and yeah, this is also a little bit annoying to compute, but you can do it if you, so here is your function. And now now you plug in here your W, right? You plug in what if it's a special convex combination. So that also might be a nice exercise for you if you want. I will not do the computation because it's a bit lengthy, but what you get is really the difference of these two models, which then get multiplied with the data. And what matters even more is that the whole thing here is still relatively complicated, but what really matters is that there is a minus in front of it, and this quantity that we saw is non-negative otherwise, right? Because it's a norm squared here, and then lambda is of course a number which is positive between 0 and 1. So everything here is non-negative, but the minus in front of it makes this a negative quantity, which is what we want, because we want to show that it's smaller than 0. Smaller or equal is good enough for us. Is the idea clear for this one? Very good. Then again, it requires a bit of compute, and the lambdas make it a little bit tedious. So what we'll actually do in full details here is the third way. There's a third way you can check convexity of this L. And that last way is to check if the derivative, the second derivative of your function is curved upwards. That's what it's gonna check. And this is something we can easily do together. So, and we just need to recap what the second derivative actually is in such a setting. So this is the gradient we are familiar with, but then there is the second derivative, which you usually write like this, and that is actually a matrix, a very big matrix, and it collects all these change rates, not of the original function, but the change rates of the change rates, right? So the change rate of the gradient. So if I have a gradient with respect to J, Wj, then how quickly does that gradient change? Here's the gradient. How quickly does it change with respect to I? That's what this does. So that's the ij's entry of this matrix. And this matrix is called the Hessian matrix. Who of you has already seen Hessian matrix? Very nice. Then I'm going too slow here. But yeah, I think the intuition is always useful. And okay, and what we can really do here is for mean squared error, it's super easy to compute it, right? So because we did this already, so if you go back, this is our L. So what is its gradient? We have done this actually last week. Just that I don't forget any minuses and so on. Well, it's here, but okay, let's do it ourselves. So we did this already. We said it's -1/n. So and then we had the x transpose times the error function, which was y minus xw. I hope that's correct. So if I compare, yes, exactly. So this is the gradient, and this is also what we call this error vector. So this is the gradient for a linear model plugged into the least squares cost function. So that's fine, but we don't care about the gradient here. We are interested in the Hessian. And now is maybe interesting for you. So can you help me? If this is your gradient, what happens if I differentiate it again with respect to W, because that's what you have to do obtain our Hessian, right? Any ideas? So what I marked in blue is kind of helpful because that's the only place where W appears. You can see W is appearing only linearly. I mean, it gets W is there, and then it gets multiplied by just a matrix. The matrix is actually X transpose times X, and the scaling is there as well. So what's the gradient of this gradient? Actually, I'll try to write a bit more clearly. So if you differentiate this again, it's very simple. So you just get the matrix which is in front of this variable, which is your W. So the result actually is a matrix, and which one? The square matrix, and it's just X transpose X. So this, what is this? We said the X matrix has the data point, it's rows. So this is actually yeah, now I get confused. Yes, this is a D by D matrix. So, right, let's recap what is the X matrix. It was somewhere. Here is X, right? But what we do is X transpose times X, right? So the X transpose has D rows, and times X, which has D columns. So therefore, this whole thing is a D by D matrix, and that's the Hessian, and that's what is written here. Okay, this is useful, and what we're asking here. So now we need to check if this matrix, the Hessian, we need to check if it's positive semi-definite, and this is very easy. Because we know basically by definition that this is a Gram matrix, right? Which is the same matrix multiplied with itself. So we know that this matrix is PSD, right? So how do you check if a matrix is positive semi-definite? Does anyone remember? You're saying there's no minus. That's true. Thank you. I need to delete the minus, but I deleted everything. Sorry. Now it's correct. All right. Thank you. Yeah, and how do we check if a matrix is PSD, positive semi-definite? Sorry, say again. Yes, you're saying the inner product defined by the matrix. Another way of saying that is just I put some vector left and right of it, and I check. I put the same vector left and right. So V, and then I put my matrix. And then I put V again. Sorry, I need to put the transpose of the V on the left and the V on the right. And what I'm asking is if this thing is bigger than 0. That's what it means for this matrix to be positive semi-definite. So I think that's what you meant with inner product. And now, yeah, why is this true? Does anyone see that? So for any V, we have to prove it for any V. Why is that true? Yeah. Yeah, exactly. So because this is the same vector on the left as this vector here. So what this is just xv, which so this is a vector squared, and of course this is a non-negative number. So we're good, except my handwriting is not so good. So, and we have proven that this matrix XX transpose is positive semi-definite, and of course every ground matrix is. So we have shown this. So we have shown that the Hessian is positive semi-definite. So that's the last way that we discussed to show that something is convex. What's also interesting here is that the Hessian of our L, it's actually a constant function. It doesn't depend where you are, which W. It's always this constant thing, which is just the ground matrix of the data. In this case, right? For deep learning, that's not true, but for a linear model, this is true. In this case here, where we have square loss. All right, so we have obtained that this is positive semi-definite, and that's what we wanted to prove. Any questions on these 3 ways to check if something's convex? Yeah. Yeah, you're saying, could I also go and check if the eigenvalues are non-negatives? That's, if I could, then yes, that would solve the problem. And you're right that, yeah, this is a symmetric matrix, so I can diagonalize it. But I don't know, I cannot do it by hand. I don't know how to diagonalize this matrix because I don't know what's in the data. So, but numerically in Python, you could do it, yes. You could also check it this way. Actually, yeah, this is how it's checked in practice, right? Here we were just very lucky, right? But if you have a deep learning model or so, then we would do what you say. You compute a Hessian, and then you compute its eigenvalues and look at them. If you see a -1, you're not convex. If all of them are positive, then you're good at this current point where you are, but that's only a local information. So, very good point. Great, so we have done half the work, right? So in our program, we said we have to do 2 things, check if it's convex. And then second thing, set the gradient to 0 and solve for W. So now we go to point 2, and we already know what the gradient is because we needed it along the way. So now let's do it. Let's set the gradient to 0, and that's this second thing on our to-do list. So. And this, yeah, we have seen this several times, right? It's just this, just X transpose times the error vector. But now we are finally going to do something useful with it, right? In gradient descent, we use this to do steps, which is also useful. But here we're now going to use this to set it to 0. And so that will be a kind of even a more drastic requirement, because we will see that we can do this, just this one set of equations, and then we will see if we can solve this for W. And so, yeah, and this equation for the case of linear models is called the normal equation. And why is it called this? Because if you look at it, it kind of means that 2 things are orthogonal to each other. Namely, what are these vectors, right? So the thing on the right is clear. That's just our error vector. It's by the way, it's in n dimensions. But what is the thing on the left? That's kind of our data. So, and so this is the data matrix transposed, right? So what this here is saying is that all the rows of this thing are orthogonal to the E vector. That's what this equals 0 means, right? If you just look at one row, it means that row of X transpose times the error vector is 0. So that's what these equations mean. So what are these rows of these objects? So it's not a row of X, right? It's a row of X transpose. So what that actually is something like here. So that's a column of your original data matrix, which means it's a feature vector. So for every data point n, so you look at one feature and you ask what is that feature for every data point n. So that's what a row here is. So so this is what we call a feature vector. And this guy, of course, is also in n dimensions. All right. So if we find a W which satisfies this, then we are good. And now, and this maybe some of you already know how to solve this because this is a linear system, and this we will discuss a little bit more in a second. But first, we'll think a little bit more of what it means, like geometrically, right? What does it mean that this is orthogonal, right? That they have inner product 0. So what does that mean? So as we already said, right, it means that every row of this thing was orthogonal to the E vector. And yeah, this row of that thing, they were actually the columns of X of our data. So that's why these are the objects which are orthogonal to our error vector E. And so that's what we already said. And that's also what is said here. And if you want to illustrate this a bit better, then you have the error vector is actually this thing here, which goes from Y to X times W. So here is X times W. And this is the error vector, right? Because it's Y minus XW. So that vector is the E, the purple vector. And so this object we're talking about should be orthogonal to any columns of the X data matrix. And that, yeah, if you ask something to be orthogonal to all the columns of your matrix, that's the same as saying that you want it to be orthogonal to the span of this matrix. So S here is the span of the data matrix. And that lives in of course, again, in n dimensions. So I think span you have seen, so it's nothing special. So this is just, it just means if you ask what's the span of a matrix A, it's just a set of all vectors, linear combinations of these columns, which I will just write this by using some weights. I can use any weight vector I want, which I call W. So and this is in D or whatever how many columns the A has. That's how the span is defined. And this, well, it looks a bit complicated here, but it's just asking what is the geometric situation, and then what does it mean that we have minimized the L, right? So what we don't see yet here is what does this have to do with L, which was our original objective. So originally we wanted to minimize L, right? So and yeah, can someone tell me what is L of W in this picture, right? I mean, the Y, of course, is given, the labels are given, the data is given. What we don't know is which W should we use. So what do you see L of W? This is this quantity. Do you see it somewhere in this picture? Yes. Exactly. So L of W is the norm of the E vector. Remember this from the slide just before. So it's just squared norm of E. That was by definition, right? So least squares is defined like this. So it's defined to be the norm of the E vector. It doesn't mean if there's a 1 over n in front of it or so. It doesn't matter here because we are minimizing this length of the E vector. And that was the vector we already had in the picture here, right? From xw to y. So what this is saying here is that the best W is the one which makes this thing smallest, right? That's how it's defined. So what it's saying is that you should find a W weight with such this point here, which is moving around, such that this point is closest to the point Y, right? Closest to the true labels. So that's how you should move around in this red plane, right? The red plane is all the linear combinations of data columns, right? Of these columns of the X matrix. So which combination is the one which is closest to Y? And that's exactly what this problem is here. And geometrically it means you asking which is the point in the right plane which is closest to Y, and that's all. So that's the true solution. So just a geometric interpretation of this optimization problem, and it also tells us what these normal equations mean, because the normal equation was saying error vector is orthogonal to X transpose. So, and that just means that, yeah, the best point here is the one which actually makes this thing, makes the error vector orthogonal to the right plane. That's what the normal equations say. So here's normal equation. It tells you that you should pick this U thing or orthogonal to the plane. So U is XW. Okay, so that's an additional way, alternative way to solve this problem geometrically, because we know what the closest point in the plane is, right? Of course, it's the one which is orthogonal to the Y. That's, by the way, also the same thing as if you would take the Y and project it onto the red plane, and everything in the plane is described as a combination of the X columns. Okay, this is the geometric picture, and then after the break we will gonna look a bit at how to solve this numerically, right? How to actually obtain the solution. It's quite easy. We have to actually solve the linear system. So let's do that. Okay, we have seen that it's 3 ways to show the convexity, and then we have shown the geometric interpretation of this explicit solution, right? And then now we also want to talk a bit about how to find this solution efficiently. So that's what is our next task. And so, right, geometrically we know what's happening, right? We know that the solution is the one which goes here, which is orthogonal to the red plane, makes the error vector E orthogonal to the plane. And yeah, what that means is this here. That is what the normal equation is. So now let's see what happens if we solve the normal equation. So what's going to come out? Can we solve the normal equation for W? And of course we can. That's going to be easy to do because we said already this is a linear system. And where is this? So how do we solve a linear system? So anyway, let's write it down again, the whole thing. So the normal equation was data matrix transpose times the error vector was equal to 0. So that's what we want to solve. And how to solve it? Solve for W. Yeah, this is easy, right? Because we can just take all the W terms onto one side, and then we have X transpose Y on the left side, and we have then we have this gram matrix X times X. That's we have on the right side, and then we're almost done. So now we have this this D by D matrix, as we said. And now we just need to, this is a linear system, right? This is matrix times vector equal to a vector. So you all know what a linear system is, so we just need to solve it. So okay, and if you assume, so if you can invert this matrix here, then this is all very nice and easy. So that's what is happening here. We just invert it, and that's one way to directly solve for the best W. So the inverse here, right, means the matrix gets inverted, and then here is this thing on the right side. Yeah, I mean, here it's on the left, but in a linear system, we call that the right-hand side, the vector on the right-hand side. Okay. Okay, then now we have the perfect W, so that's a solution to the problem. And then, yeah, if you want to ask, how can I use my model? Because this is a bit a complicated expression. So you can also use this expression to directly predict new data points you have never seen. So if you want to do that. So here is a new point. So that's what you would call a test point. You have not seen this in your training set, but still you would like to make a prediction of the test point. And of course, the prediction is always just X times W. And then if you plug that in, you get this. Times the vector. So just to understand that this, you can also use it to predict new data points. So, okay, but there is actually one bit problem which is a bit more interesting, is if this matrix with the data in itself is actually invertible or not. So we should be a bit more careful here. We just assume that it's invertible, but what if not? So because the data matrix can be absolutely anything, right? You never have much control of what your customer or whoever. So what they give you as a data matrix. So some data matrices are tall and narrow. So for example like this can have this shape here. So I mean, the data matrix is always n times d, right? So and then when you do the x transpose, then sorry, you do x transpose x, then that would look quite small then. So this is one case. But of course, it could be the other way around, right? If your customer gives you a data matrix with more features than data points, which is perfectly possible, then this X transpose X matrix might be gigantic. It's again D by D, but then it's going to be much harder to assume that this matrix is invertible. So it's not going to be clear. Very likely this will not be invertible. So that's what we need to discuss a bit here, so that if we can actually take an inverse or not. So I mean, we will see that even if you do not have inverse, we can still solve the linear system. There is a way to solve it. But what is interesting is that if it's invertible, then everything is much nicer, because then then the solution at least is unique. So that would be very, very convenient. So okay, when is this thing invertible? It's invertible if the X matrix has full column rank. It just means if it has full rank, so that the rank is D, right? Here it has fewer columns than rows. So in this example here, that seems okay, because D is much smaller than N, right? So there's a good chance that this matrix has full column rank. It's not for granted, right? But it's usually it would have this property, but you still need to check it. And then in the case here, when you have many more features than data points, then it's actually not okay. So here it's never possible. This matrix will certainly not result in an invertible XX transpose. It's impossible, right? How can this matrix have full column rank? How can it have rank D when it has only such few rows? So because the rank will always be smaller than the smaller of the two, right? Either the rows or the number of columns you have. So that's one thing. So you're not always invertible, but I guess you're already familiar with this. And then if you want, there's also a small proof here to if you want to convince yourself that if the column rank is okay, that yes, that means that X transpose X is invertible. So this is actually if and only if condition. All right. Now, if it's not, then what do we do? And that's exactly the case here when we have more features than data points. That's exactly what I already discussed just now. So that and if again the X matrix then looks like this, when D is much bigger than N, and that is realistic, right? It's not that this is very rarely happening. And what we call this here is that we say the model is over parameterized, right? Because we have D parameters in our model, but we only have N data points. So it's over parameterized. There's more parameters than data points. So it's not necessarily a problem, but this is a very interesting property and also very common in neural networks that you have more parameters than data points. And then even in the other case here, so even if you have more data points than features, even then you could have the case, for example, that you have twice the same column, and or it could also be that just one of the columns happen to be all zeros, so that the feature is always 0 for any data point, and then also you have a rank which is too slow, so too low. Even if the shape of this matrix looks convenient to have rank D, it might not, because one column might be duplicated, one column might be 0, lots of things might happen. Okay, so if you don't have this full rank, then you cannot build the inverse. So the question is, can we still do something? Can we still find maybe not this solution, but can we find a solution to the problem? And yes, so I mean, what you're going to do is, of course, you just still solve the linear system. If I remember correctly, yes, this is the linear system. So which you can solve, right? So you compute this vector here. You of course have the matrix, and you feed that to a linear system solver, which is using some smart algorithms to solve any linear system and to find one of the possible solutions if there is one. So and actually you will see in the lab, there is in NumPy there is already linear system solvers integrated. So you can try this. And the good thing is here, you don't need to worry at all, right? No matter what your data is, it's always going to be okay, right? The linear system will always find you a W, even if there are many of them, right? So there is always a W, which is the minimizer, right? There might be several, right? But it's never the case that there is no solution, right? That's actually a special property of this system here. If you would just ask this, then I think here it could be that there is no W which satisfies that it's exactly Y, right? So not every linear system has a solution, but this is a special linear system because it has the X kind of on both sides, and this one always has a solution. So because it's a D by D matrix, and we have D variables, so there is always one solution, but there might be several. So, and the linear system solver will do its job, and then it will depend a bit how good is it going to work, how fast is it going to be. That's going to be depending a bit on the what we call the condition number of this matrix. So the condition number is telling you if you have a matrix it tells you how well it is invertible. So it's invertible, but how close is it to not being invertible? So if you just change it very little, could it become non-invertible, and then you would have a problem. So the condition number is defined on the eigenvalues of this matrix. Actually uses the largest one and the smallest one. So largest eigenvalue and smallest one, lambda mean, of this matrix, whichever you want to ask. For us, it's the Gram matrix. So I'm just giving you this quantity and telling you that this quantity is a bit is telling you how well the linear system solver, how quickly it's going to be finding a solution. And also here you see that this condition number becomes infinite because lambda mean here becomes 0 if you don't have full rank. So if you rank deficient, then the condition number is not defined. Then the denominator becomes 0 and the whole thing blows up to infinity. Okay, but yeah, in practice we are not worrying so much about it because we will just solve the linear system anyway, and that's what I suggest for you to. In practice, you will always just build this system, feed it to the solver, and you will get one solution W. Okay, so if we summarize this just quickly, we have now seen a lot of different methods to solve this fundamental problem, to train these fundamental linear models. In particular, 3 of these things were grid search, then gradient descent, and the last one was from today, the closed form solution, that because it's linear plus least squares loss, it's a very easy structure. We can write down the closed form solution with this gradient 0 trick, and that is possible for this particular model class. So you can use all of them. Of course, the grid search is not going to be so practical, especially in high dimensions, and people use both these methods extensively. So the nice thing about the gradient-based methods is that they were much more broadly, right? You don't need to care that if it's really exactly the least squares loss on exactly this model. I mean, you can always run gradient descent even for different losses and so on. And this one here is even better because it's even faster, but it's really only for this exact type of model. And why is it faster? So yeah, does anyone of you know the computational cost let's say, of building the inverse. So if we go this way, right? If you compute the inverse and then with this, so what is going to be the cost to compute W? Any suggestions? Order of something depending on N and D. So what's the cost of a matrix inversion? Is I hear D square, other suggestion, I hear D cube. So, and what's the size of the matrix? So that we need to invert. It's a D by D matrix, and indeed, inverting a D by D matrix is actually D cube. If you do it naively, I mean, there are better algorithms. There's some algorithms. Especially if you go via the linear system, then there will be faster algorithms. But if you do it naively, then it's D squared. And so that's for building the inverse. But there's another thing that we actually need to first form this X transpose matrix. So that's also, yeah. First, this thing has to be computed, which is also not trivial. So how much is it to compute X transpose? I hear N by D square, which is correct. Because yeah, one of the x's is N is X, sorry, is N by D, and you multiply it with itself. The result is a D by D matrix. So that's to form the X transpose. And then this is for the inverse. Okay, so it's not so cheap, but the good thing compared to gradient descent is that here you do this once and you're done. You have the exact and final solution. But if you do gradient descent, then you have to do many steps, and we don't know how many of them. We said one step of gradient descent is also relatively cheap. Actually, a full gradient step is also going to cost a bit like this. But the thing is that we have to do many steps. So that's why if you have this, then this will be fastest. Especially if you use a good linear system solver, because those are even faster than D cube. The linear system solver are D to the power 2.4, if I remember correctly, so they can be very fast for even large values of T. So okay, so these are the 3 ways to solve least squares problems. And any questions on this? Now is the time. Okay, if not, I will quickly go to overfitting and underfitting. This is a bit different, but we will use the same example to study it. And this is very important because, yeah, these are really both of these phenomena. They happen all the time when you do machine learning. And it's really, again, it's exactly depending on that, how many data points do I have, how many features do I have, how easy is it to fit the model to get a good cost function. So it's important to get a good feeling to how underfitting and overfitting works. So, and thanks, someone on Zoom told me that it's not linear systems 2.4, n to the 2.4. Actually, they tell me it's a 2.37 is the world record to solve linear systems. If that's correct, I think. I trust you. The people try to make this always a little bit faster, but nobody has found a way to solve it in n squared. So, okay, what is underfitting and overfitting? So when we cannot make the model fit well, when it's far away from what it should be, I mean far away from the labels y, then we say we underfit. And then if it perfectly fits the data, on the other hand, if it fits the y's as perfectly, but it even fits to tiny small variations which are not even desired, which are actually, the data might have noise, right? So maybe it's actually not a good idea to get perfect 0 error or 0 cost for every data point. So So then if you have this error, but you really made your model much too fine-grained, much too complex to fit your Ys, then you again have a problem. So both of these phenomena are problems. They're both not desirable. And now we need to discuss a bit more precisely what that means, and then later also how to avoid it. Actually, overfitting is quite easy to avoid once you have observed, once you have detected it, right? But what you have to be careful about is to really make sure you check, you're sure if it happens or not. And the underfitting can also happen a lot. It happens if your model is not powerful enough to possibly fit it, or it also happens if your training just failed, right? I mean, maybe there is a good model, but your learning algorithm, the optimization algorithm, didn't find it, so then you also get to underfit. So what's really important for you, I think, here is to keep an eye on it and to detect it, that you're aware that it could be a situation where I'm underfitting or overfitting, and then take the right countermeasures. So, and yeah, let's see this in a concrete example, and we again go for the easiest one we always play with here. Is that you take a one parameter model, and that's the one, the parameter is just W0. So in the real numbers, of course. So this ignores the data, and that's the red line. So this model here is what it is, but you can, I think you would agree with me that it's not a good model to fit the data, which is the blue points. So the blue points, that's what your customer gave you. They gave you this whatever 10 or so points. And so what you can think is that maybe if you would get more data, then maybe it will come from something like the green model. I mean, just speculating, right? But what you see is only the blue points, and what you see is that how well is your red model, how well is it fitting those points, and that's here. So this is the E vectors for each data point, which we are always using, right? So you can see that the error values are pretty high for most of the points. Some of them are okay, but not all of them, of course. Okay, so this is a question of underfitting, of course, and now let's try to find a better model for this. So, so, and to do this, so this is just one-dimensional data, right? The x is a number. So maybe I should have said that. That's actually the most interesting thing. The data is one number, and so is the model. So even if the data is just one number, then can we use linear models to make something a bit more elegant, something a bit more powerful than this red line, right? Is there a possibility here? Because obviously the red one is a bad model to the data, but we only have one feature. So is there a way to get better linear models? And that's something that we can do, is to actually augment our data to make more features, to then have linear models on this larger number of features, and they hopefully will be a bit more powerful. So that's what it means to do feature augmentation. And this is a really common thing to do. So, and that's also really what you will see in the lab on Thursday. So it's quite simple what's happening, right? So here is your original data point, xn, right? It's just a number. So can you expand it to have more features? And what we suggest here is to add, well, here's the feature you already had. That's the number here we have, but now you add some more. You add one. The adding one as an additional feature, we already saw that as a trick, right? We saw this, that there was a trick that if you want linear models to have this shift, then that's a trick to do it, to then use 2 parameters instead of 1. So that's what happens if you take 2 features instead of 1. So that's one way. And then you go further, right? You can add more nonlinear functions of this original feature. And the easiest nonlinear function is just maybe take it to some power, take it to the power of 2, power of 3. So that's certainly something you can do. I mean, you have really full freedom in designing additional features to use, right? Maybe from your use case, the X was, I don't know, it was maybe it really depends what makes sense to represent these features. If it's the original number, or if it's maybe the logarithm of this number, right? If it's, I don't know, if it's like sound energy or something that someone gives you, then maybe it might be a good idea to use the logarithm of this original feature instead. So, and that's perfectly fine. It's a good idea to use that. Or maybe you want to use the sign of your original X, and you can use any of these you want. You can use the positive part of your X, and then also make another feature for the negative part of the same thing. So it's just a creative way to make more features. And so that's the freestyle way. But then the systematic way is actually here to use what we call polynomial features, which is just the original one taken to the power of m, or whatever degree you choose to use. So these guys here are called the polynomial features. So. Or polynomial feature expansion if you want. So before we had one feature, and now we have a new feature vector, for a new data point with more features, and that one has m+1 features now, which is quite convenient. And what we do then is now we have now we do a linear model on these expanded features, right? So again, here is the W with the original features. You can do it. So originally we just had this part, right? 1W times the original xn. And now we have many more W's when we do a linear model. So all these guys, and here is my expanded feature vector. And that's a way to expand features and then apply linear models. It's really the most natural way to do it. You can always do this. And why is this interesting? Because now it looks a bit more powerful, right? Now we have a model which can express much more interesting functions of the X. So actually now this thing can express any polynomial in the original X. Depending, now you have lots of interesting weights W to learn, not just one. You can use all these weights to approximate the true labels you want to fit, right? Here we were not able to fit them. So maybe here by using this type of model, it's a much more powerful model. Maybe that model will be able to fit it better than the original one. So this is my new model. So yeah, it's FW of my data point, but now it's of the expanded data point, which is like phi xn. I mean, you don't need to call this phi, right? You could just say that, okay, this phi is now my new data set. You had an all data set, one number per data point. Now you have a new data set with m numbers per data point. Does that make sense? So yeah, basically the all data set was just this x1. This is the all data set, and now the new one is much bigger. It's a this was just one feature, and now I have m plus 1 features. And again, data set is always n data points. So okay. And then we do regression on a new data set. Let's see what happens if we do this. And you can see that if you just look at the pictures, you can see that it's getting a bit more interesting. So what we do now is we just adjust this m, right, the degree. So we adjust how many additional features do we want, right? The m, is it, I mean, it can be just 1, then you're basically in the original case. It can be 0, then that's the case we had on the very first slide. And it's getting a bit more interesting when it's when it gets to higher degrees of your polynomial. So, okay, so the first picture here is the parameter, one parameter model we already had. So, and that corresponds to using a degree 0, right? Because we don't use any x anyway here. And then the second one here is the 2 parameter model. So, and that means we have a W0 times nothing plus W1 times x. And that's exactly here, right? I hope I got this correct. Yes. So that's if you take m equal to 1. So that means that every data point has these 2 features. One is this shift, and then x was the original value. So this is m equal 2. Sorry, m equal 1. And that means it's 2 parameters, right? Because you have 2 blue parameters. So that's here, and the effect is what you expect. So yes, it can actually learn something a bit more powerful. So that's FW of x. So now the red line is much more interesting. I hope you agree with me. It's a bit better. It fits the data a little bit better, the blue points. It doesn't fit super well. The first model where it's actually fitting rather well is this one, which is the 4 parameter case. And in that case, so now you go up to here, right? For every data point, you use these 4 numbers. 1, the original value, then the value squared, and the value cubed. So that's the 4 parameter model. And that's how it looks like. By the way, this is all in the Python of your lab this week. You can play around with this yourself. But now the red curve looks pretty good. So right. So the red line is always FW of x, right? And now here you see it fits the data quite well, the blue points. And what's even more important is it seems to follow the same pattern as the green line. So the green line is trying to indicate where the data truly comes from, right? We don't know in reality. But if you had infinite data and no noise, then you might ask, maybe there is an underlying model where nature has generated this data. So there might be such an underlying model. Maybe these blue points have come to be by taking a sine function and then adding a bit of noise. So that could have happened. If that happened, then here we're trying to find some red model which is close to the truth, the green one. And this one does seem to be pretty close. But what's more interesting is happens if, well, it's not perfect, but what we really are interested in now is what happens if you go further. So this is a 10 parameter model. So we go with the feature expansion up to the degree 10. So x to the 10th power, that is going to be the last feature you can use. And then you learn the W's for it. And then it does this crazy stuff, right? So, I mean, what's interesting here is it perfectly does fit every data point. So there is 0 error. So the error is usually, I don't know, you can show it in black here. So it was pretty big in the previous models. It was rather small in this good one here. That was wrong. And there is absolutely no error in the 10 parameter model. It perfectly fits every data point. So the cost, if you do mean square, the cost is 0. So it's nice to have 0 cost, right? It sounds good, but there is a problem with it, right? So the problem is that the test error might be crazy, right? If you say L0, that just means that the training error is 0, right? So training means you fit the blue points. But what happens at testing is maybe someone gives you this one new point, and now you see your model is like totally wrong. So this one could be an illustration of the test error. I mean, usually the test error is an average over many points in a test set, but here I just pick one test point, and I don't know what's going to happen in reality, but certainly if your red model makes such crazy high and low values, it could happen that you might be very far away from the truth if you make a prediction on a new point. So that's the black line, right? How big could the test error be? And on the other hand, if you're in this good model on the left here, maybe if I get a test point here, then it will have rather small error. This is a point I've not used in training. It comes from the same green distribution, has very small error. But here I can have a very large error because I choose a very, very complex model, a degree 10 polynomial, for something which the truth would be quite simple. It's a sine function, but it's noisy. There's a little bit of noise, which you always have in real applications. So then what happened is that our model was kind of too powerful, so it has fit not only to the green, but it has fit also to the small noise. And that small noise made it go to a crazy shape, which made it then behave very differently on the training set, the blue points, compared to the test set on the black points. I just use one test point here, but it would be the same if you have many. Yeah, I hope this is somehow a bit clear, at least intuitively. So what this says is that, yes, overfitting can happen even with linear models. So here in the first case, we had underfitting when we had just m equals 0. And then on the end, we had overfitting. And so what is really, this is not necessarily a bad thing. This is actually a good thing that we observed both extremes. The good thing, I actually, this is practical advice that if you do machine learning, you should actually always do overfitting and also do underfitting. You should see both. Because if you see both, then you actually know that the best thing might be in the middle. So the best model is in between, right? So for us, the best model was this one here, which is the 4 parameter one, but we don't know. But thanks to us really trying all the M's, these are we call this like the model class, right? What is the family of models which are even candidates, right? So we tried complex candidates and we tried easy candidates, and we found one candidate in the middle, which was really good both in training and in test. So that's why this is the best model, and that's why we will go for this one. And actually next week we will be more systematic. So about exactly this process. So this process is called model selection, right? Which model should we use? So here you want to use the best model here. There is a very small thing before I let you go. So is to how you avoid overfitting. So now you have this problem. What do you do to avoid it? One way is to just make the model simpler again. So then you go here. So that's usually what we always do. We make the model simpler, or we kind of add regularization or dropout in deep learning. But if you don't want to make your model simpler, then there's another way to reduce overfitting, and that is just to have more data. And more data also solves the problem of overfitting. So if you have extra data, then you can fit very complex models. So here is again m equal 9. So very same complex model as we had before, but it's not overfitting because we have now much more data. So 2 ways to fix overfitting. One is simpler models, and the other one is more data. So, and with that, I will see you on Thursday.